We're continuing to solve our example 3D truss problem represented by this diagram here. In our last video, we completed step 3 of our solution process. We assembled the global stiffness matrix from the various local stiffness matrices found in previous videos. In this video, we'll continue on to the 4th step, applying boundary conditions. We'll also complete the 5th step, solving for the unknown displacements. So again, in our last video, we found the global stiffness matrix, and I represented it by this table here. As you can see, the global stiffness matrix has that same symmetric form that we've seen throughout this course so far. Okay, this is as a table we're used to seeing as a matrix. Let me present it as a matrix. And in applying our boundary conditions, what we're going to be doing is remembering what the purpose of this matrix is. We multiply this matrix by the displacement vector, and it will yield the force vector. Okay, so here's my displacement vector. This is my global displacement vector. And when I multiply this first column by U1, the second column by V1, the third column by W1, and so forth, then the resulting, remember this represents 12 equations, will solve for the force applied to the node 1 in the x direction, the y direction, the z direction, node 2 in the x direction, y direction, and z direction, and so forth. So what we do in apply boundary conditions is we take the values we already know about our problem and we insert them into the displacement vector and the force vector. For example, I don't know the displacements at node 1. I'm trying to solve for U1, V1, and W1. I do know the displacements at node 2 in the x, y, z direction, as well as the displacements at node 3 and node 4. These are all pin joints connected to a wall. These points or these nodes are not able to move, so I know that U2 all the way through W4 is 0. Likewise, while I don't know the resulting or reaction forces due to the wall at node 2, node 3, and node 4, I do know the forces applied at node 1. I was given the value of P, 20 kilonewtons in the x direction. I was also not told anything about forces applied in the y or the z direction. I can assume those are 0. So inserting that information, I am now left with this system. All right? At this point, I will say that I've completed step 4. I've applied boundary conditions. I'm ready to move on to step 5, solving for my unknown displacements. Now, it looks like we have a lot of math to do. We have, see, 12 by 12. There's a lot of zeros in here, but forgetting about the zeros, that's 144 different mathematical operations to figure out what all these different numerical values are. But if you look a little bit more closely, you'll see that if I'm multiplying this column by U1, this column by U2, V1, and this column by W1, I'm multiplying this column by 0 and all of these columns by 0. So I don't get any interesting information by these columns. Also, only the first 3 equations represented by the first, second, and third row involve U1, V1, and W1. So I only need to look at this simple 3 by 3 system represented by this vector, representing the 20,000, 0, and 0, U1, V1, and W1, and these 9 components of my global stiffness matrix. All right, so let's zoom in and look at that problem. All right, so here's that problem. I have a matrix I know the numeric values of. Remember, I created these by taking the numeric values for the various components. Remember, when I take these values and each one of these is a sum from 3 different local stiffness matrices, don't forget the coefficient in front of each local stiffness matrix. Okay? So again, I have a known matrix. I have a known vector. I'm looking for unknown U1, V1, and W1. I can solve this by hand. I can write this out as 3 equations and 3 unknowns and use substitution. I can use my calculator, or I can use MATLAB. Whatever method you use, you should find that a displacement of U1 of 1.3 times 10 to the negative 3 meters. V1, I got negative 5.119 times 10 to the negative 5 meters. And W1 equals 6.015 times 10 to the negative 5 meters. Again, this was one of the things the problem statement asked us for. On my homework, I'll want to put a box around that if I want full credit. So we're done with step 5, solving for the unknown displacements. Some of the times I've included solving for the unknown reaction forces as part of this step, but you'll note in this particular problem we weren't asked for those displacement forces, so I won't worry about those now. We'll move on to step 6, analyzing the solution. In this case, that is finding the stress in each element in our next video.